Okay, one of the last sort of historical things I wanted to tell you about was the speed of light. As we know from some of our past lectures, the speed of light is quite fast. We have some numbers out there like 1 foot per nanosecond. If you've taken a physics class recently, it's 300 million meters per second, or 186,000 miles per second. You know, something like that are the numbers for the speed of light that we sort of all know and love and agree on these days, but it wasn't always so easy like that. In fact, the speed of light has a very long history, as sort of shown in this table here. So what you can see is it maybe started around 1600 with Galileo and sort of proceeded all the way up to, this chart's kind of old, but about 1973. And what has happened, of course, is the estimate for the speed of light has just gotten better and better and better and better until, if you look all the way down at the bottom here, 1973, the number is actually pretty close to what it is now, and with a very small error in there. And you can see there's a bunch of techniques that people used: rotating mirrors, carousel, microwave interferometer, all sort of things here. And some of these things we even do these days in advanced physics labs for our students. But if you look in particular here, Romer, 1675, used the moons of Jupiter to measure the speed of light. And I just wanted to tell you what that was about. So this is sort of what Romer proposed to do here. If Jupiter here is this orange planet right here, Jupiter has a bunch of moons around it, which we'll talk about in some upcoming videos here. But say there's a moon here, the first moon, Io. Okay, Io is, of course, orbiting around Jupiter, and so suppose it orbits like this and goes behind Jupiter and comes back and sort of goes like this and keeps doing that in its cycle, right? So it's doing an orbit, its orbit. So here's Io, goes behind, comes in front, goes behind, comes in front. What Romer looked for, he looked for these points right here where Io would disappear and reappear. Those are like events that one could look for. And so here's what he did. He said, okay, suppose you're in the orbit around the sun on Earth, because that's of course where we all are. So this is the Earth's orbit right here, going around like this. And suppose we're at position H. If Io disappears behind Jupiter, say right there, and you're at position H, then light only has to travel more or less this distance to reach you right here. So this distance here, and I'll just label distance to reach you. And Romer would time it and so on. And then what he did, he waited a whole half of a year for the Earth to continue its orbit around the sun, as you know, and go all the way down to position E right here, all the way down here. So what has happened now is he's now this much further away from Jupiter, which is basically 2 times the radius of the Earth's orbit. So if this is right here is 1 radius of the Earth's orbit, and this distance right here is another radius of the Earth's orbit, he's fully two radii of the Earth's orbit away. So he's getting basically another sort of 2 AU, as you know, away from Jupiter now. And so what he was hoping or expecting here is that this time would be small or smaller, and this time here would be large. Just because of the increased distance this disappearance events would have to take before we'd actually see it happen. Remember, when you're watching these reappearances and disappearances here, those are little events that you would have to see with your eye. And so if you're here, you would see it happen. Relative if you were here, you would see it happen, but it would happen later because you're farther away. It should take light longer to reach you. And so let me just show you an animation about how that worked. I'll go over to here, and I have an animation queued up here. So this is basically the sun. This is the Earth's orbit, and this is Jupiter right here. So if I run it, you can see that here's the light. These looks like little, I'll run this a couple times. Let me just set you up here. Here's Jupiter, and here's the Earth. Okay, Jupiter's the red ball. There's the Earth. There's the sun right there. And what these little balls are that it looks like they're shooting across aren't bullets or missiles or anything. That's say light, or say like photons coming from one of those disappearance or reappearance events, right? And so if you watch the video, let me cue it up again, you can just tell that when the Earth is very close to Jupiter, as well as over here, it doesn't take as long for the light to reach it as it does when the Earth is, say, way down here, okay, very far away. Now the times are getting shorter and shorter and shorter as we're very close to Jupiter. Wait half a year until we get very far from Jupiter, and the time would be longer. So Romer indeed noticed that the eclipses happened at slightly later times when we were farther from Jupiter than they did when we were closer to Jupiter. And so that is a bit of a historical bit about how Jupiter's moons were used to find the speed of light. And this is just another summary table of how it sort of all happened, the history of the measurements of C. Here's Romer. He got about 220,000 1,000 kilometers per second, which is, in the ballpark. But even as it got better and better, not even still in antiquity, 1700s, 1800s, down like that, the numbers got better and better. But indeed, Romer did have a first good stab at it by using the moons of Jupiter. So moons of Jupiter for speed of light measurements, one of the original ones.